Good morning. Welcome back to EELE 461, 561 Digital System Design. And this lecture is for our meeting time on Friday, April 3rd. And what we're going to do is continue our look at crosstalk. And this time what we'll do is we're going to look at inductive crosstalk. So last time we looked at capacitive crosstalk and we looked at how the current was injected due to an electric field coupling, and that manifested as current that was injected into the victim, and it split and went both ways. And so that was cool. In inductive crosstalk, the coupling mechanism is magnetic fields. And so if you think about a wave propagating down the aggressor, you have the magnetic fields that look like this. The lines look like they operate or they move, clockwise around it. And this is the right-hand rule where you put your thumb in the direction of the wave. And so in this case, the wave is going into the screen. And with the way that it couples onto a victim, as you can almost think about it, like makes this flux over here that starts pushing magnetic field lines that go in the same direction. So as this line up here comes around and it goes down, it kind of like starts pulling a magnetic field line in the same direction, and it kind of starts to swirl over here on the victim. And so what happens is that you get magnetic field lines that flow in the opposite direction on the victim. And so if you use that right hand rule for the victim, what happens is that you can think about your thumb is coming out of the screen on the victim. And so what does that do in terms of current? Well, you have an aggressor B field that's heading down this way, okay, like into the screen. It's actually going to create a current in the victim that is flowing the exact opposite way. And so that's a lot different from capacitive crosstalk, where you injected current and it split equally and went both ways. In this case, it's going to create current in the victim that only flows one way. Okay, what does that mean in terms of crosstalk? Well, it's interesting because if you think about going into the near end, so the current's going to flow down here and go into a near end impedance. And remember that across a passive device, you have a plus and a minus, and if you have current flowing into it, that is the definition of a voltage being induced across it, a positive voltage. Well, down here on the load, your model is an impedance connected to a ground or a return, but the current is going the exact opposite. It's coming out of the resistor. Well, that's the definition of a negative voltage coming out of a passive element or a passive impedance. And so you actually will get a negative voltage at the far end. The positive voltage at the near end is going to be very similar in shape to the capacitive crosstalk, because once again, as it builds and flows down here, it's like this coupling mechanism is like a voltage source that's traveling down the aggressor, and the whole time it's coupling over onto the victim. And then as soon as it couples, it starts flowing down here. And so by the time that the aggressor wave hits the load, it's still coupling on, and it finishes coupling on to the victim, but then that coupled current still has to flow all the way back down here. So you're going to see that characteristic kind of blip of voltage that is spread across 2 TD. Okay, so let's look at the the model. So we have our LC model of this, and we have our mutual capacitance coupling here, and now we're going to add in our mutual inductive mutual inductive coupling. And so you have this little LM in there, okay? So the way that mutually inductive coupling works is it's the same equation for an inductor, where you have a voltage across, induced across an inductor is equal to inductance times di dt. But you use the mutual inductance, for the coupling. Okay, and this is a representative. LM is basically how strong the magnetic field lines are coupled. And then you use the I in the aggressor, but you're looking at the voltage that is induced in the victim. Okay, so you notice that you have VM is going to be over here on the victim. LM is this little fella, and then I, the DIDT, is actually the aggressor. But then once it gets over here, you have this inductance over here, and you go, well, how much voltage does that generate once that current is injected and starts traveling back down the line? Well, it's interesting because then now you're basically this current right here where it's traveling backwards, and which it would be IB in this case. I call this IA and this IB. And it is now inducing voltage across the line inductance of the victim. And so it's kind of an interesting thing. So the coupling that gets the energy over into here uses this equation. Vm is equal to Lm di dt. So it's the current here that induces a mutual voltage over here. But then once it's over here, the current that is created, or the voltage that's created, actually generates this IB that flows back down here. Okay, so whole bunch of math. It's like, well, the voltage, you know, that was mutually coupled is put across an inductive element on the aggressor. So those voltages are equal. And what you're trying to figure out is how much current did that create that's going to travel down the line and create a voltage at the near end. And so you can plug in the voltages where you have Lm di dt using the aggressor current. That's equal to the line inductance times IB dt, which is this current that was induced. And then you can come in here and you can say, oh, how am I going to get rid of this delta, you know, the di dt? Well, what's the t and what's the v, right? So you can plug in t rise for t dt, and then you can convert that into a voltage by, you know, now you're sitting down here where you're trying to figure out, I want a voltage, so you multiply the I by Z, and that'll give you a voltage. And in the end, what ends up happening is you kind of get back to this ratio where once you start moving the terms around, you get this Lm over LL is equal to VB over BA. And because what we were doing right here is we were trying to convert all these currents into voltages. And so how do you convert a current into a voltage? Well, you can multiply by the impedance, and then you have this time component in here, and you say, what's the dt? Well, the dt is always t rise. So anyway, and now you end up getting back to this ratio that we wanted, which was you couple over VB is what you see on the victim, VA was what was on the aggressor, and it's a ratio that looks like Lm over LL. So you take that, and that gives you your V near end crosstalk over VA, and so there's your ratio that you care about. But then once again, we're at the near end. So it's going to jump up to that level, and it's going to stay there for 2TD and then go away. And so once again, you have a factor of 1/2 that accounts for the spreading out, and then you have a factor of 1/2 for the forward reverse traveling component of it. And once again, you have this 1/2 in there, even though, you know, you have a 1/2 for the time spread, and then you have a 1/2 for the actual that it's like that it's spread out distributively. I don't know if that makes sense. Okay, so anyway, now let's go down, look at the crosstalk on the far end. Now this one is nutty because it's got that same characteristic shape where you're kind of like building up this wave as you go, but it's negative, right? And then you have to account for the entire wave that's built up along the aggressor transmission line. And so you have this length over velocity times t rise again, and then you have your negative component in there. Okay, so those are the equations there. So let's put everything together. So now we have full near-end crosstalk, and you have this near-end crosstalk coefficient next. And like we said with superposition, you just add them together. So next is the basically a percentage of what you're going to see of the aggressor voltage. So you have V near end over VA, and it is 1/4, and you have your capacitive coupling, and you have your inductive coupling component, and we sometimes call this KB. And now if you look at that, these two add together. So this is the B comes for backwards coefficient, and you have that characteristic wave shape right here, but you actually add them together from capacitive coupling and inductive coupling, so this thing gets bigger. Okay, all right, that's cool. But here's the weirdest part. If you look at far end crosstalk, the inductive crosstalk is actually negative. And so if you look at this equation, you have this Cm over Cl minus Lm over LL, and then you have this, you know, component right there. This is also called Kf, or forward traveling coefficient. And what's crazy about this is that if these ratios of the mutual coupling component to the line characteristic were the same, you would actually cancel out the crosstalk, and you would have the forward, the positive blip due to capacitive coupling and the negative blip due to inductive coupling. They would cancel out. And so it's like the craziest thing ever. It actually turns out that if you contain, this is kind of a sentence here, if you contain all the field lines within a homogeneous dielectric, okay, then these ratios will be the same. Now you go, what in the world is a homogeneous dielectric? So think about, it's basically the same dielectric everywhere the fields flow. And so what would be an example of that? Well, think about like a strip line transmission line on a printed circuit board. You have a line and you're completely surrounded on all sides by FR4, and then above you is a ground plane, below you is a plane. So, and all the field lines are contained. That would actually result in no far end crosstalk. If you were a microstrip where you are on the top of a printed circuit board and your E field is most of the time that it goes up in the air, it's in air, and then it comes back down, and then it goes into FR4 before it hits the return plane. Same thing with the B field. So you have like this circular magnetic field around you, but the top half is in air and the bottom half is in FR4. That is not homogeneous. So you tend to only see far end crosstalk on microstrip transmission lines, and you can get rid of it when you have strip line transmission lines. Okay, so that's it. That's kind of a rough overview of crosstalk. So again, watch this video, and then I have a short little quiz for you that will be due on Monday at 9 a.m. And have a good day.